So remember that our sequences are just an order of numbers that are in a particular order, and they follow a general rule. And for our arithmetic sequences, we added a particular constant each time to our number or the previous term. For our geometric, it's going to be very similar, but this time we're going to be multiplying by a constant each time. So in general, our definition for our geometric sequence is going to be a series, a set of numbers where each term is determined by multiplying the previous term by a specific constant. Now that constant is going to be called our common ratio. And just like before, it seems kind of backwards that we're calling it a ratio, even though we're multiplying. But remember that in order to be able to find that ratio, we would have to divide two of our consecutive terms in order to be able to find the ratio. So in general, just like with our arithmetic sequence, we have a formula that can help us find the nth term or any term in our sequence. And it's given to us by a sub n equals a sub 1, which remember is our first term, times r, which remember is that common ratio, to the n minus 1 power. So because we are multiplying by the same number each time, it can actually be rewritten using an exponent instead. So let's look at an example. It says, write an equation for the nth term of the geometric sequence. So in general, we said that our equation is a sub n equals a sub 1 times r to the n minus 1. Which means in order to be able to write a general equation, we need to know our r value and we need to know our a sub 1 value. Well, if we notice in the list, they give us our a sub 1 value as 0.5. And then we would need to find our r value. So we just need to take two consecutive terms. So like if we took 8 and 2 and divide them. And remember, we want to divide the larger term by the smaller term. And when I say that, I don't mean the value of the number. I mean that our 8 is further along in our sequence than our 2 is. So we know that our r value is 4. So we plug that in and we say that it's 4 to the n minus 1 power. And then we could use that formula to find any term in our sequence that we needed to find. Now our next one is a little bit different because notice they give us the fourth term this time instead of the first term. So we're going to have to do a little bit of work to find that first term this time. Now notice that they do give us the fourth term, so we're going to use that value, so that's going to replace our a sub n. So we have 5 equals, we're looking for a sub 1, so that stays as a sub 1. they tell us that our R value is 6, and we used 4, or the fourth term, for our N. So we would have 5 equals a sub 1 times 6 to the third power. 6 to the third power is going to give us 216. And then we're going to divide in order to find a sub 1. Now 5 over 216 does not reduce, and it's not going to be a very pretty decimal, so we're going to go ahead and just leave it as a fraction. So in general, our a sub n formula is going to be 5 divided by 216 times 6 to the n minus 1 power. And again, we could use that formula to find any term that we wanted to find. Now, in general, remember that a series is basically taking the terms of a sequence and adding them together. So a geometric series is going to be the terms of a geometric sequence added together. And just like with our arithmetic series, we can find a partial sum of that. And our formula is given to us by s sub n equals a sub 1 times 1 minus r to the nth power divided by 1 minus r. So let's go ahead and look at an example of this. Now, we talked about summation notation in our last lesson, so it comes up again and we can still use it. We just need to interpret it a little bit. So we still want to be able to use that formula. What's a giveaway that we're talking about a geometric series in this case is that we have an exponent on the inside of our summation. So that tells us that we want to use that partial sum formula that we just had. And then we need to find a couple of things. So my a sub 1 we can find by plugging in the first number that they tell us to plug in, which remember is the bottom number. So that's going to be 3. So we get 4 times 2 squared, which gives us 16. And then remember, we also need to find our R value, and your R value is going to be whatever is being raised to the power. So 2. And then our N, remember, is the top number minus the bottom number plus 1. So we get that N equals 8. Once we have all of those numbers, we can go ahead and plug in. So we have 16 times 1 minus 2 to the 8th power divided by 1 minus 2. So simplifying that, we get 1 minus 2 to the 8th power divided by a negative 1. Plugging all of that into our calculator, then we should get 4,080. And that would be the partial sum of the first 8 terms in that series. Now, what's different about our geometric series is that we also can have an infinite geometric series. So an infinite geometric series means kind of what it sounds like. There are an infinite number of terms in a geometric series, which remember means it's going to go on forever. Now, if it's a convergent series, that means that there is a sum for an infinite series. And if it's a divergent series, that means that there is no sum. Now, this sounds a little hard to imagine because we're talking about an infinite number of numbers that when I add them together, I'm going to get a single number. And because up until this point, when we talked about our series, we were talking about like with our arithmetic where we took 2 plus 4 plus 6 plus 8. The more things that we added, the larger my number got. And so we couldn't say that if I just had an infinite arithmetic series, it's not going to be able to be convergent because my sum is just going to get larger and larger and larger the more numbers that we add. But if we look at something like the example that we have, so we have 0.3 times 0.03 times 0.003 and so forth. So notice that if we were to sum all of these together, we would get 0.3 repeating, which hopefully we recall that 0.3 repeating can be rewritten as 1/3. Now notice though that if we were to round this number at any point, notice that this does not equal 1/3 any longer. It can only equal 1/3 if I have all of the terms in the series. So we can kind of think about it like our asymptotes. If we were to keep adding these together, so our asymptote would be at 1/3. And as we added our terms together, our numbers are going to get bigger and bigger and bigger, but they're slowly going to approach 1/3. And we can't say that it ever reaches 1/3 if we were to cut it off. In order for us to reach 1/3, we have to have that infinite number of terms. So it says to determine whether the each infinite geometric series is convergent or divergent. Now, the biggest thing for us that we need to know is an infinite series is going to be convergent if r, or the absolute value of r, is less than 1. It's going to be divergent if the absolute value of r is greater than or equal to 1. So we need to find our R value in order to be able to tell if it's going to be convergent or not. And remember that we can find our R value by taking two of our terms and dividing them. So in this case, I have 36 divided by 54. If we were to reduce that fraction, we get 2/3. Notice that 2/3 is less than 1, which from our rule above tells us that we know that this series is going to be convergent. So looking at the next example, we have 8 plus 12 plus 18. So again, we have to find our R value first. So we would take 12 divided by 8, which is going to give us 3/2. Well, note that 3/2 is greater than 1 this time. So our series will be divergent. Now, in general, if we have a convergent infinite series and we want to find the sum, we have a formula for that. So it is the sum equals a sub 1 divided by 1 minus r. Notice this time we don't have a subscript for our sum because it's not a partial sum this time, it is the overall sum. So it's just s. And also notice that they do point out that our r, if it's greater than or equal to 1, the series will have no sum. So it says, find the sum of each infinite series if it exists. So our first step that we need to find is our R, because that's going to tell us if the series is convergent or divergent. So we're going to start by taking two of our terms, so 6 divided by 15 divided by that first term, which is 2/3. Notice that we have a complex fraction, so we need to keep our first fraction. We're going to change our division to multiplication, and we're going to flip that bottom fraction. And then we can go ahead and reduce. So notice that 2 goes into 6 3 times, and 3 goes into 15 5 times. So we end up with 3/5, which is less than 1. So we know that this series is going to be convergent, so we can go ahead and use our formula. So our sum formula is S equals a sub 1 divided by 1 minus r. Our first term is 2/3. We found that our r value is 3/5. And then we just need to simplify. So notice in our denominator, if I have 1 minus 3/5, it's the same as having 5/5 minus 3/5. So we get 2/5. Again, we need to keep our top fraction, change our division symbol to multiplication, and flip our bottom fraction. When we do that, notice that we have a 2 in the numerator and in the denominator, so we can reduce those. And so our overall sum is going to be equivalent to 5/3. Let's look at another example. So we can also see infinite series in sigma notation. The only difference, though, is notice that in our top spot, we have an infinity symbol. So instead of going to a particular number, we're starting at 1 and we're going to infinity. Now remember that when we look at our sigma notation with our geometric series, we said that whatever is being raised to the power is going to be our R value. So in this case, our R value is 4/5. Well, 4/5 is less than 1, so we know that it's going to be convergent. So we just need to plug into our formula. So our sum formula tells us that we have a sub 1 divided by 1 minus r. We already know what our r is, but we do need to find our a sub 1. So we can go over to the side and do a little bit of work. So we're just going to plug in our first number, which in this case is 1. So notice that we have 1 minus 1, which gives us 0. So we would have 4/5 to the 0 power. Thinking back to our exponent rules, remember that anything raised to the 0 power is going to be 1. So our 4/5 to the 0 power will be 1. We then multiply that by 18, so we just get 18. Now plugging in all of our known values, I have 18 divided by 1 minus 4/5. Simplifying that, we will have 1/5 in our denominator. So we end up with 18 times 5, which gives us 90. So we know that the sum of this infinite series is going to be equal to 90. So remember, your biggest thing about your sequences and series is knowing your formulas and knowing when to use which formula. So you need to remember, if we're talking about a sequence, we need to use our sequence formulas. If we're talking about a series, we need to use our series formula. And for our geometric, you need to make sure, if you're looking at a partial sum, that we use our partial sum formula. And if you're looking at an infinite series,